Hello and welcome. In this video, we're going to talk about a case study which will give us the hands-on experience of working on different types of regressions, starting from the basic ordinary linear regression to ridge regression and lasso regression. We will also be able to compare the performance of these regression models and understand how these work in a different way. For example, in our theory videos, we've deliberated a lot on the differences between ridge, lasso, and the ordinary linear regression. You'll be able to see all of that happening live in this case study. This case study has been obtained from a site called Kaggle, which is a popular site for computations, and this case study is titled Fish Market Analysis. Essentially, the case study is about predicting the weight of the fish. So why is it important for people to predict the weight of the fish? Is there a possibility that we can get to know more about the weight of the fish given certain attributes? That's what we are going to look at. So fish, like many other products, is often sold by its weight. Customers would want to pay for the fish based on the weight and, of course, certain other aspects like species. The objective of this case study to understand what are the factors that lead to the accurate prediction of weight. We've been given certain features. We're going to put them into a model to be able to predict the weight. So from a consumer perspective, they see it as more value of money if they're able to get a good bargain. That is, by spending less, they're able to get a heavier fish. There are also assumptions related to the taste and texture of the fish based on its size and weight, which are popular among seafood enthusiasts. Here is the dataset. This dataset talks about these features. First is species, which is a categorical feature. Then we have three different types of lengths, which are measured in centimeters: vertical length, diagonal length, and cross length. Then we have height, and then we have width, which is diagonal width in centimeters. Finally, we have to predict the weight, which is our target variable, and this is measured in grams. So with this, let's now dive right into the coding piece. All right, so here is our Google Collaboratory, and I've already pointed to the data source, which is available on my local machine. Now, we're going to start step by step. I'll explain you every single line of code, and this case study would have a lot of interesting takeaways for us, so stay patient and stay put. We're starting by importing the necessary libraries. Apart from the basic libraries, we'll also be needing classes like lasso, ridge, and linear regression from the sklearn linear model. We are suppressing the warnings related to packages. We begin by reading the data. Since we've already pointed to the data source, it'll be very easy. Just using the read CSV, we have read the data. Now we can check the first few observations just to get an idea about how does the data look like, right? So as anticipated, species was a column which was supposed to be categorical. You can see this has strings in it. Then the rest of the columns have all numbers, and these in particular are floats if we talk about, because they have decimal values. Let's check the last few observations just to check if it's more or less consistent the same way everywhere. Yes, that seems the case. Now we can look at the descriptive statistics of this data. Right now, we'll only be looking at the numerical variables. So if you see, we can get an idea about the minimum and maximum value and the different quantiles of these variables. One quick observation here, which is an anomaly, looks like we are predicting weight, but it says the minimum weight of the fish is given as 0. So this could be an anomaly. Why would somebody buy a weightless fish? We may want to check how many such records are there where the weight of the fish is listed as 0. So to do that, we'll just apply a filter on our data frame. In our original data frame, we are pointing to the column called weight, and we are checking wherever it is equal to 0. So this double equal to in Python represents equality check. A single equal to represents assignment. We are checking for those records which have the weight mentioned as 0, and we are doing a shape 0, which will lead to the number of rows that we have where the weight is 0. Let's check. So it looks like there is just one such row which has the weight listed as 0. And since this does not make sense, we can simply ignore this record. How do we do that? We can filter our data frame for all the weights which are greater than 0 and store it as the same data frame so that that one record that we originally had will automatically be ignored. Now we can check the info of the data frame, which often gives us the information about the dimensions of the data, the data types, and the null values, if any. As you can see, we seem to have 158 records, and we don't seem to have null values overall. The data types are appropriate as anticipated earlier. So in a way, from this place itself, we get an idea that we don't have missing values. But if we want to specifically check for each column, we can just run a simple for loop. We are going over a list of column titles, and we are saying we want to check is null.sum. Is null.sum basically gives us the sum of missing values by each column. When we run this, no surprises, it was anticipated to be zeros everywhere because we don't seem to have null values anywhere here as well. Now we are just trying to detect the presence of outliers in our data. And we know that outliers would make sense only for the numerical columns. So we have segregated only the numerical columns, leaving aside the species column for the time being. And we are running a loop over the length of this list of numerical columns. We've given a plotting area, which is 1 row and 6 columns. So all these 6 features, these numerical features, would show their box plots next to each other in the same row. And this would be nicely separated using tight layout. So let's see what happens when we run this. You can see that these are the box plots starting from the weight to length 1, length 2, length 3, height, and width. These are the box plots for all the features. As we can see that some of these box plots indicate the presence of outliers. In fact, out of 6, 4 features have outliers. Now, it's one piece that we have outliers in the data, but are the outliers so many that they can really affect the analysis? We'll have to check the number of outliers as well. And how do we do that? So we are creating a temporary subset of the overall data, which will ignore the species column. We are calling it df_num or df numerical. And we are writing a simple function, which will take each column as the input, calculate the Q1, Q3 values, which are 25th and 75th percentiles, the difference between these values, which is nothing but the interquartile range. And then it will return the count of those values, which are less than the lower limit or greater than the upper limit. We are summing it up. So we are just trying to check in any direction, if at all we have outliers, what's their count like? One feature at a time, we'll be able to check it for all the features. Now that this function is defined, what we're doing is that we are applying this function to our numerical data frame. See, this function would not make sense for a categorical data. That's why we initially segregated the species column. And let's run this. It will tell us feature-wise how many outliers we have. So looks like we have 3 outliers present in weight, 3 outliers in length 1, length 2, 1 outlier in length 3, and that's all. Like I said, the number of outliers is very limited. So we're not sure if this really has an impact on the central tendencies right now, especially the mean right now. Because if you have many outliers, they will tend to skew the distribution towards the higher or lower values, depending on where they are located. But when the outliers are limited, we may not see such a significant difference, and then we may leave them untreated. But in order to be able to do that, we should at least compare the mean and median. We know that median as a central tendency does not get affected by the outliers, whereas mean gets affected by the outliers. So in such cases, for any feature, if we find out that the mean and median are too separate, then we will go about treating the outliers. Otherwise, we may just choose to ignore for such a small count. So how do we check the mean and median? Very simple. Once again, we are putting it through a loop. So we are going through the list of numerical features, and we are saying for each feature, we want to calculate the mean, round it off to 2 decimal places, median, round it off to 2 decimal places, and a space after that. So see how the output comes. So we get to know for weight, looks like there is a huge difference between mean and median. The mean is 400, whereas median is 281. But for other columns, if you see, these values are pretty close, 26, 25, 28, 27, 31, 29, 8.99, 7.79. These values are pretty close. So we would not really have to worry too much about other columns. In fact, we should look at only these 3 columns, I think, because this is where we had outliers. So these values are pretty close. Even for the other columns where the outliers were not there, the mean and median are not identical. We don't want them to be identical. They're close. That's good enough. So barring this column weight, we don't seem to have a serious issue with the presence of outliers anywhere. Now let's check in the weight column, how much is the impact of these values which are outliers, those 3 outliers. So first of all, what we're doing is we are calculating the upper limit beyond which the values are declared outliers for weight. And you know the formula for this is Q3 plus 1.5 times Q3 minus Q1. Let's get this weight above which the values are outliers. This is 1,443 grams. Now what we are doing is that we are checking the indices of those values which are nearly above 1,445 or 43. We can change it to 43 to be precise. Let's run this. Okay, so this results only 3 index values, which means there are only 3 such records in our data which have these values greater than 1,443. We could see that earlier as well, but now we exactly know which all rows contain the weight which is greater than 1,443. So now what we are going to do is we're going to simply drop these outlier values because these are very limited values and they seem to be influencing the target column. We don't want to work with them. We will simply drop them. Once we do a df.drop with these 3 indices, let's check the rows after that. It should show a difference of 3. That's what it is. We had 158 rows to begin with, and now we're left with 155 rows. So this is about the numerical columns, which seem to have no missing values, but had outliers, and we've kind of checked that. Let's quickly inspect the categorical column. The only categorical column that we had was species. So we may want to look at the value counts. And in fact, what we can do is we can create a quick bar plot with appropriate title and X and Y axis labels just to check how does it look like. On the bar itself, we are putting the counts or the number of occurrences of each category. So here is the count plot. So we can see there are different species that are present, and they have different number of occurrences in our data. Very few whitefish to maybe a very high number of perch and everything else in between. The unique entries in species are these, as we can see on the x-axis as well. Now, species is a column which is categorical, but we don't really have an order in mind for this. We can't say that a particular type of fish is always going to weigh lighter compared to another type of fish. Maybe the experts can comment on that, but as of now, we don't have that intelligence available. So in such cases, when we have categorical columns and we don't really know a sense of order with those columns, we would want to convert these columns into one-hot encoded columns. Now, what is one-hot encoding? We're going to treat every single species as a separate feature. This can be easily achieved using the getDummies method in the pandas library. So what we're doing is that we are checking the number of columns in the original data frame. When we just do shape, it returns rows and columns. So when we pass index 1, it is going to return the number of columns. Without any one-hot encoding, what's the number of features? And once we do this one-hot encoding, what will be the number of features? Notice, whenever we do one-hot encoding, we generally drop one level. It has been explained at length in the videos where we've covered the concept of encoding. So you can refer to those in case you need further clarity on this. But we've just dropped one of the levels of the categorical column, and then we are checking the modified number of columns that we'll have once we apply the encoding. So as you can see, we had originally 7 features. Now when we do one-hot encoding, we have 12 features, and this is how the data looks like. So one-hot encoding is going to result into such columns which will only contain zeros and ones. One, when a particular variety or species of a fish is present, otherwise it will always be zero. These are the original numerical columns that we had, which are as is. So if we check the features, we have introduced these new features. As you can see, species, along with the species title, it has a prefix, which is the original feature title, to indicate that this is another representation coming from the original species column. Now, as you can see, we have such variables which are only zeros and ones, and we have other variables which are on different scales. For example, we have values in hundreds of grams. We have values in centimeters, which are varying in tens and units. So what we want to do is we want to bring the variables to the same scale. Now, this may not be mandatory for linear regression's performance, but it is always a good idea if you want to compare the coefficients. The variables on the same scale always helps. Let's do this. What we're doing is a standard scalar. We had very few outliers and hardly having any impact on the mean. So we can go ahead and apply the standard scalar, which is going to fit the data to a standard normal distribution. We have selected the list of features, and this would only make sense for the numerical columns, not for the encoded columns. Once we apply standard scalar, when we do this fit transform, it tends to convert the data into an array form. But we find it more convenient to work with data frames. So this fit transform thing is something that we are storing inside this data frame, and we are giving the appropriate column titles as well. So let's see how does the scale data frame looks like. So see, these are the first 5 columns of this data, which were on a very different scale. And now you can see most of these values have been normalized. Now you can see most of these values would fall between a -3 to 3. That's how a standard normal distribution is supposed to look like. Now, since we have the scaled version of these variables already, it'll be wise to drop the original variables, which were unscaled variables from the data frame. And notice we are also doing a step here, which is reset index, because in the original data frame, we also had eliminated a couple of rows. So those indices would be missing from the data. Why it is important at this stage is because in the next step, I'm going to concatenate the scaled data frame with the original data frame, which has the one-hot encoded representations. Now, if I do not do a reset index, the scaled data frame would come up with continuous indices from 0 to whatever the last index is. But the original data frame would not contain all the indices because 3 indices were missing. We dropped those rows. So just to make sure that this concatenation works properly, we have done a reset index before doing concatenation. So once we've done with that, in this particular case study, we are not focusing too much on validating the outcomes or accuracy of the model. We are more interested in taking away the interpretations and comparisons between linear regression, ridge regression, and lasso regression. So we are not partitioning the data into train and test samples. We're utilizing this entire data to create the model, because the objective is not to prove that we can create accurate models. The objective is to understand the underlying concepts a little better. So let's do the customary X and Y split. So we are taking all the independent features, leaving aside the Y variable or the target column, and we are separately storing the target column as Y. And now we are going to utilize these classes that we originally called from sklearn linear model, linear regression, lasso, and ridge. And we will also be comparing their R-square values, which is something that we've explained at length in the theory video on linear regression. So the custom steps are that we instantiate the model, we fit X and Y values. If there would have been a train test split, we would have fit only on the train data. But since in this case, we did not do that, we are fitting on the overall data. Once we fit, we are going to do a predict. And then for generating the R-square value, all we need is the actual target column and the predicted values. This is going to be the same process for all three types of regression. Instantiate the model, fit it, rate the outcome, which is the model performance measure. So once we generate these R-square values for linear regression, ridge, and lasso, we are just printing them, rounding off to 2 decimal places. Let's see what are the R-square values looking like. So linear regression seems to be giving a 95% R-square, ridge is giving a 94, and lasso is giving a 94. Like I said, we don't have to worry too much about the R-square value right now because there could be a lot more to it as we progress. But for now, let's try to do a comparison between the coefficients. Remember, the whole idea of ridge and lasso was that ridge and lasso try to control the coefficients. Let's see if there is a difference in the kind of coefficients we get for all these three models, right? So what we're going to do here is that we are going to call the coefficients of each of these models. This ridge is nothing but the ridge model, and lasso is the lasso model. So when we do a dot coef underscore, it returns the coefficients of these models. We are rounding up all the coefficients to 2 decimal places. And in order to be able to compare them conveniently, we are creating a simple data frame, which will contain the index as the name of the model and the features as the original features. Just bear with me for a few seconds and you'll be able to appreciate this outcome. See, this is what we got. This code here has led us to this output, which is very easy to compare for all three models. So when you see this output, you can see that, let's say we talk about length 1, length 2, and length 3. The coefficients are very, very different between these models. For example, the coefficient in case of linear regression for length 1 is negative, length 2 is a positive value, length 3 is again a negative value. Whereas if you see the ridge regression, it has given nearly an equal weightage to length 1 and length 2, but length 3 has been given a relatively much lesser coefficient. And if you look at the lasso regression, it is considered length 1 as a high coefficient, length 2 is much smaller, and length 3 has been reduced to 0. Remember, we discussed that ridge regression can reduce the coefficient to a very small value, but might not reduce them to 0. Whereas lasso regression is capable of reducing the coefficients to 0, which makes it capable of doing feature selection. Likewise, there are other coefficients as well, which have been minimized to a great extent. For example, species has 2 specific categories, which have also been eliminated by the lasso regression. These values were reduced to a negative minimal value by ridge, but these were not reduced to 0 by ridge. So as you can see, all these models behave differently. Lasso, apart from just fitting a regression, is also able to do feature selection. Out of the original 11 features that we had, it has eliminated 3 features and reduced some of the other features very close to 0, 2.98 or negative 3.75. But 3 features have been completely eliminated. Whereas if you look at the ridge regression, it continues to maintain all the features as they were originally passed. And of course, so would be the case with linear regression. Now, one interesting aspect that we did not explore earlier on purpose is correlations. Let's check if these features that we started with were correlated. Remember, linear regression is always sensitive to multicollinearity. So to check the correlations, I'm taking only the numerical columns and checking the correlation values through a heat map. if you see the original data had a lot of strong correlations. So for example, length 1 has very strong correlation with length 3, length 2. Length 1 will obviously be correlated with length 1, and we don't really mind length 1 being correlated with weight because that is our target column. So any correlation between a target and independent variable is not a problem, but any correlation between the independent variables would generally be a problem. We've not taken any proactive measure in this case study to treat the correlations, but let's see to what extent the lasso and ridge models are able to address this, if at all they are able to address this, right? So you can see lasso is able to very finely segregate between length 1 and length 2. It's not giving them equal weightage, and it has completely dropped length 3. Let's look at length 3 here. So length 3 had very strong correlations with all the features, with length 2, length 1, and of course with weight. So length 3 has completely been eliminated. Lasso is not a technique dedicated towards treating multicollinearity, but it has been able to penalize the coefficients to an extent that some of the coefficients that were correlated either have got reduced weightage or have been completely eliminated. Ridge also kind of tried to do that with length 3, but between length 1 and length 2, it's kind of giving an equal weightage to both. So these two models, if you see, definitely have in some way addressed a little bit of multicollinearity problem as well. Now let's move on to creating a plot between the actual versus predicted values for linear regression. So what we are saying is we'll take the actual values that were given to us with the data and the predicted values that we've predicted using our model. And we are just trying to create a plot to see how these look like. If they are very nicely correlated, it would indicate that the model is very good. So in this case, if you see, this red line represents the linear regression, and these are the points around it. So there are some points which are a little far, but most of the points are pretty close, and that's why no wonder your R-square value was really good. Notice in this case, this alpha is not to be confused with the tuning parameter. This alpha represents the transparency of these points that we showed. So if this alpha is not made transparent, these would look like darker blue circles, not to be confused with the hyperparameter. Okay, let's see if we can look at the ridge outcomes in a dynamic sense. Now notice this alpha here is the tuning parameter. This is not the one we're using for transparency. So keep this in mind, not to get confused. See how to read this plot. These are the actual Y values and these are the predicted values. If everything is in sync, then all these points should fall on this red line. But if we change the value of alpha, and we've seen this in the theory videos, if we increase alpha, it is going to penalize the coefficients a little more, which means if I increase the alpha to a greater value, it will reduce the fitment of these points to this line. This line would not be doing justice to these points anymore. Let's see. So you can see more and more points are moving away from the line, which is an ideal match between actual and predicted values, right? Similarly, if I reduce the value of alpha, you can see points will move towards the line. More and more points are now fitting the line. So changing the values of alpha would affect the outcome. This alpha is a hyperparameter, also called lambda in some of the books and references. This is the tuning parameter, which is multiplied to the sum of squared coefficients in case of ridge regression. Let's also see how would the coefficients for ridge look like as we increase the values of alpha. So that comes next, and we'll be more interested in its output. If you see, as the value of alpha increases from 0.01 to 1000, 10 to the power minus 2, to 10 to the power 3, you can see how these coefficients are all coming close to 0, nearly 0. It may not be very clearly visible here. You may think these are exactly 0, but it would rarely be the case that ridge reduces the coefficients to exactly 0. These are nearly 0, and some of them have come to much smaller values. Remember, the whole idea of penalizing the coefficients was when you have a problem of overfitting. So this just shows as a scope that the values of the coefficients would vary depending on the value of alpha or lambda, or the tuning parameter as we call it. Let's check the same aspects for lasso regression. So once again, here is the output and the same explanation. If everything is in sync, then this red line would be the line which has all the data points lying on it. But obviously that's not the case. Increasing the value of alpha, even in case of lasso, would move these points a little away from the line. The fitment of these points to the line would reduce because the model is becoming more generalizable, right? And if we reduce the value of alpha, you would see that the points are coming closer to the line. So increasing the value of alpha would reduce the fitment. Reducing the value of alpha would bring them closer to the point, which means the predicted and actual values are fairly in sync. Once again, let's understand how would the coefficients behave in case of a lasso regression if we keep on altering the values of alpha. So for a very small value, which is 1 over 10 to the power 2 or 10 to the power minus 2 or 0.01, to a very high value, which is 10 to the power 3, you can see again. The difference between this plot and the one that you saw for Ridge is that you do not see these values coming almost close to 0. In fact, some of these values have exactly touched 0. This line represents the coefficient value as 0. So when you take the value of alpha to a very high value, almost all the coefficients will be reduced to 0. We generally don't take it to very high. We generally don't keep it to too low. We do a trade-off. And in our example, you could see we did not really tune the value of alpha in our case study. With just the default value of alpha, it was able to reduce at least 3 coefficients to 0. 3 features were eliminated. Remaining were selected. So we'll see more on this piece as we take the next case study, which will be involving a relatively more complex dataset. For now, the major takeaways from this case study were that we understand that the coefficients are different in case of linear regression, ridge regression, and lasso regression. And we specifically explored the property of lasso regression, which leads to feature selection. Hope this helps you get a little more intuitive understanding of the advanced form of regressions. In the subsequent videos, we'll delve a little deeper.